here we go. So we talked about systems of linear equations, right? Systems of linear equations had two lines that intersected, right? They intersected at a point. That was our solution, right? Well, now we can also have systems of linear inequalities, meaning we will have more than one linear inequality. So yesterday we talked about linear inequalities and graphing them. Now we can graph two linear inequalities in the same plane and see where they overlap to see what solutions they share. So let's start with the basics. A system of linear inequalities is just like a system of linear equations, except for it's two or more linear inequalities, in the same variables. A set of two or more linear inequalities in the same variables. April? Yes, x and y. So usually it's an x and y. It's usually like y is greater than something x. And then another one's like y is less than something x. Yeah, okay? Okay, so we talked about yesterday that the solution to a linear inequality is an ordered pair that when plugged in makes that inequality true, right? So the solution, a solution to a system of linear inequalities when plugged in, that ordered pair, must make both of the linear inequalities true, okay? So let's write that. The solution to a system, I'm not going to write the whole thing. The solution to a system is any ordered pair which is, of course, x comma y, any ordered pair that makes both inequalities true. So let's look at this first. We're just going to sort of look at plugging in some ordered pairs, seeing if they're solutions or not, by plugging them in to the inequalities. So this is example 1. And it's going to basically ask us, is the ordered pair a solution? Is the ordered pair a solution? Here's our system. Y is less than 2x, and y is greater than or equal to x plus 1. So we're going to use this system. This is the system of linear inequalities because it is two linear inequalities in the same variables, right? So first they want us to check, is this ordered pair 3, 5 a solution to this system? So we're going to just do the same thing that we were working on yesterday. We plug in 3 for x and 5 for y. The difference is now we need to plug in 3 for x and 5 for y in both linear inequalities. Okay? So let's start with this one. hold on, I'm going to number them. All right, so if this is number 1, let's start with number 1. Okay, we'll plug in y, 5, is less than 2 times x, which is 3. 5 is less than 2 times 3. When we simplify, we get that 5 is less than 6. Is that true? Yes. So far, so good. It is definitely a solution to one of our 2 inequalities. So then we need to also plug it into the other one, because we can't say that it's a solution to the system unless it works for both. So then we'll take inequality 2, which says y is greater than or equal to x plus 1. So we'll plug in 5 for y, greater than or equal to 3 plus 1. And we get that 5 is greater than or equal to 4. Is that true? Yeah, 5 is greater than 4. So both of these inequalities, when we plug in that ordered pair, we get true statements. 5 is less than 6. 5 is greater than or equal to 4. So because the ordered pair creates a true statement in both of the inequalities, we can say that yes, this ordered pair is a solution to the system. Okay? Let's try another ordered pair. Is this -2, 0? Is this ordered pair a solution to the system? We're going to use the same 2 inequalities. Is -2, 0 a solution to this system? So we're going to do the same thing, plug it in. We'll say that 0 is less than 2 times -2. 0 is less than -4. Is that true? No. Good. No, this is not true. 0 is not less than -4. It's greater than -4. So we can stop right here. Because it is not a solution to one of the inequalities, it's not a solution to the system. Okay, it has to work for both in order for us to say yes. So we could stop right here and say, no, we know this ordered pair is not a solution to this system of linear inequalities. Okay? All right. Let's talk about graphing these. All right, the graph of a system, I'm going to abbreviate, of linear inequalities shows all solutions of the system. So then to graph, what we need to do is we're going to refer back to our steps from yesterday. Follow the steps for graphing each inequality. So you're going to have to graph each boundary line correctly, right? Dashed or solid, and shaded correctly. Make sure you shade correctly, because that's how we see what solutions the inequalities share. Okay, and then the second half is you're going to shade to identify where the solutions overlap or intersect.
Is there a possibility that the answer could be no solution?
There is a possibility, yes. And we'll do an example like that. April? Yes. You'll use your graphing calculator to help you find the line, and then you're gonna basically be doing what we did yesterday, but 2 different times. Okay? Michael?
How would you do that, like, if you have to write out the graph? Or do we not need to do that?
I'm going to show you. I'll show you. We'll do it like we did yesterday in the examples. So let's do one of these right now and just practice. So here, this is example 2, and it says graph this system, y less than or equal to 3 and y is greater than x plus 2. Okay, I'm going to set up my graph here. Okay, I'm going to call this one 1, and I'm going to do it in green. Okay, this graph is going to look like just a horizontal line, right, at 1, 2, 3, crossing the y-axis at 3, and it will be solid, right? So this is intersecting at 0, 3. And then I'll plug in my origin to see if I need to shade down here or if I need to shade up here. So if I plug in the origin, I get that 0 is less than or equal to 3. Is that true? Yeah. Meaning I'm going to shade down here. So I've graphed my first inequality. Now I'm going to graph this one in the same plane. So there's going to be some overlap, which is good. That's what we want. So I'll call this equation 2. And I'm going to use my calculator to help me draw this boundary line. Okay, I'm noticing that my inequality symbol is just greater than, so I'm going to remember that I need a dashed or dotted line. Okay. Let's check it out. So we'll do x plus 2, graph it, and then I will use my table to find some points. Okay, so I have an open circle at 0, 2. I have an open circle at 1, 3. 1, 2. And let's do -2, 0. So this is a dashed line then going through here. Okay, so then my last step, almost last step, this is sort of the final step that shows me where my graphs intersect, is I'm going to plug in a point here to see where to shade on which side of this blue boundary line. So I'm going to use my origin because the line doesn't go right through it, so that's going to help me figure out, do I shade here where the origin is, or do I shade the other side where the origin is not? So let's plug in 0, 0. So 0 is greater than 0 plus 2. 0 is greater than 2. Is that true? No. Which means I will not shade this side because the origin is not a solution. Instead, I'm going to shade this side. Now, it's easier to see in the book than it is in my notes, but where's negative 3, 3, negative 3? Exactly. Look at this overlap. I'm going to do it in red just so that you guys can kind of see it better. The solutions to both of these sets are the part where we are shading both inequalities. They both have shading going on right in here. Okay? So this is where they overlap. Any ordered pair, so yes, like negative 3, 3, or yeah, negative 3, 3 would be a solution because it would fall on that line, so that would work. Any ordered pair that falls in this red area is going to end up being a solution because it will be true when we would plug it into both equations or inequalities. Okay? Okay. So, Kaden, to answer your question, yes, sometimes you may have a system of linear inequalities with no solution, meaning there would be no overlap of the two graphs, and they would not share any solutions. This is example 3. So, for example, this one says y, or wait, no, it says 2x plus y, goodness, less than 1. 2x plus y greater than 3. Yes. All right, so first, let's get these into slope-intercept form so that we can graph them more easily. So y is less than negative 2x minus 1, and y is greater than negative 2x plus 3. Okay, what do you notice just by looking at these inequalities? What are these lines going to look like, Kaden? The slopes are parallel, so we're going to have parallel lines, right? So that's just good for us to know in our head. We're still going to graph them because we need to figure out where to shade. But it helps us to know that we're going to have two parallel lines here. Yes?
If they are parallel, isn't there either like no solution or like one small like sliver down the middle?
Right. Well, yes. Yes, it's either no solution or it's only one side of one line is all the solutions. Do you see what I'm saying? Because you'd like have to shade, one part would have only one shading, but then the other part would have like all the shading. But yeah, you're right. All right, so let's graph these. Let's do this as number 1. So we'll do y equals negative 2x minus 1. Put my table up. So we've got 0, negative 1, and these are all open circles. 0, negative 1, negative 1, 1, and let's do 2, negative 5. Or let's do 1, negative 3, 1, 1, negative 3. All right, so there's my first inequality, but I need to figure out where to shade it. So I'm going to plug in the origin. So I would do 0 is less than negative 2 times 0 minus 1. 0 is less than negative 1. Is that true? No. Meaning I will not shade the side that contains the origin. I'm going to shade this side instead. Okay, and then we'll graph second inequality. Plot some points. 0, 3. 1, 1. And 2, negative 1. Plug in the origin. 0 greater than negative 2 times 0 plus 3. 0 is greater than 3. Is that true that 0 is greater than 3? No. Meaning I'm not going to include the origin in my shading. So I'm going to shade this side. Right. So is there any solution that would be part of both of these? No, because they don't overlap at all. Okay, so we would say that there is no solution to this system of linear inequalities. April.
For example, would have to show this graph, and we wouldn't have to show, would we have to write like a...
Basically what it would ask you to do is graph it. Is that answering your question?
Yeah, but would we also have to put a ordered pair?
No. Okay. Nope. Because there are like infinite numbers of ordered pairs that are solutions. So you just show it using the graph what the solution set is. Okay? Okay.
Now, for ones like example 2, do we just have to put like our answer just 1 point that is on that line?
No, you would show me the graph. You'd have to show me that graph.
Oh, just the graph is the answer.
The graph that shows all those ordered pairs that could be solutions. Does that make sense? Cool. Okay. Last thing that I'm going to show you how to do is to write a system from a graph. So sort of working backwards. And you have to look at the graph and you have to write that system of linear inequalities. All right. This is example 4. It says write the system represented by the graph. Write the system represented by the graph. Here's our graph. Let's do this one first. Okay, so we've got that line going that way. Basically every, 0, 0, 1, 1, 2, 2. And then we also have a line here down at negative 2 that is solid. And they show us here that this is the only part that's overlapping of these two systems. So we need to come up with two linear inequalities that represents this graph. So let's start with which one looks like it's going to be easier. This one, yeah, the horizontal line, right? That's going to be easiest for us to figure out the equation of that. We know it intersects the y-axis at -2. So it's going to be something like this, y -2. We just need to figure out which way that inequality sign is facing, right?
We know it's not equal to.
It is an equal to. It is an equal to because why?
Oh, no, sorry, I meant the other.
Because it's a solid line. That's okay. So this one we know, like we're getting down to the end here. Now we also know that this is shaded above the line, right? So the origin is shaded. What do you think, April?
0 means
If we put 0 here, what would make that true? Very good. Right? If we put in a 0 for y, and we wanted to make it true because we know it has to be true because the origin is part of this, we would say y, or 0, is greater than or equal to -2. So this line is that linear inequality. Sophie?
So what would it be if it were less
Then it would be shaded under here, right? Because then the origin would not be part of it. Michael?
So does that mean like if it's greater than, is it above, and it's less than, is it below? Or greater than to the right and less than to the left?
Sometimes, but it depends, like,
It depends on like what numbers.
yes, I'm not going to say that with certainty. I'd have to think about it more before I give you like a definitely always yes or definitely always no. It seems like that, doesn't it? But
Yeah. Like, let's say it was above, the line was above. Because like, if y is less than -3, you shade
below it, right, right. Definitely for horizontal, yes. For horizontal, if it's less than, it's below, and greater than, it's above. Now, for lines with the slope, I'd have to think harder about it. Like if it's always on the, left side or the right side, I'd have to think a little harder. But let me look that up, because that's a very good question. It's a good, insightful question. Okay, now let's find the inequality that represents our line with a slope. First of all, let's use what we know about slope-intercept form, right? Do we have a y-intercept here? Of what? 0, right? So we technically don't need to even put anything because it would be y equals mx plus 0. Goes right through the origin. What's our slope? 1. How did you know that?
First, it's rise over rise.
Good.
Second, like, if you took 0, 0, and 1, 1, you needed 1 minus 0,
Yes.
1 minus 0.
Yes.
It's coordinates formula.
Yes. Yes. Slope formula in my room. But yes. So you could use that y2 minus y1 over x2 minus x1, like choose 2 points and plug it in. Or we could just do rise over run. And luckily, this is a fairly straightforward slope, right? Every time we're going up 1 over 1, up 1 over 1, up 1 over 1. So rise over run, it's just 1. So we know our slope, y, we're going to leave that blank, is just relating to x. There's no intercept, and our slope is 1. So we just need to figure out what goes in that space. Michael, what would you put in that space and why? Less than why?
Because the y is less than that.
Yeah. What if we pick an ordered pair in here? Like, we know these are all solutions. So let's pick an ordered pair that falls in this shaded area. Let's do 3, 1. And this is x and this is y. How are x and y related to one another? You're right.
X is greater than y.
X is greater than y. So,
Y has to be less than x.
right, if we put in an equality sign describing how these two are related, y is always going to be less than x in order for them to fall in this shaded area. Okay? Okay.